thank you very much for being here. Thank you very much for having me here. I would dare a bet, a big bet, that I had the shortest distance to come here, because as it happened, shorter than Edward, for example, if you were to go to the registration desk, that distance is larger than the distance to my office, which is that window. But there will be another distance to cover because I'm not in information technologies. I'm not an electrical engineer. In fact, I'm a mathematician and computer scientist. So I'm very grateful for the opportunity to tell you a little bit about my work. There will be, even though it's math and computer science, there will be limited formulas. So it's an opportunity to show you a bit of the things that you do algorithmically. Now, in the interest of time, I cut out the joke that there's no AI in this. If you're curious about the AI joke and robots, I'd be happy to share that after the talk. So one of the things that when you're working on computers is that you realize that it's no longer that you have one computer, and of course that's a connection to networks, but an important part is how do things scale. And I do a lot of geometric work in large and small scales. And as it happens, a human, a standard human, this is a small size human, Danny DeVito, who is about 1.50 meters, is about halfway in terms of orders of magnitude between the sun and a hydrogen atom. And we don't go all that way, but some of the things we have been looking at are super small particles. That's a 50th of a millimeter, that's a microbe. And of course, we also look at constructing large structures like this so those are the dimensions we're looking at. And in fact, we do have projects in both of these. In that case, we don't work with Darth Vader, but with NASA, and we hope that there is a distinction. So very small size, very large numbers, and very large sizes. And one of the things is when we're looking at structures and organizing structures at extreme dimensions, turns out that there's a similarity between being 1.50 meters or 80 or something like this, and looking at very, very small dimensions or very large dimensions, you're equally far away. And then when you are trying to control a system, understand the system, control the system, change the system, reconfigure the system, it's actually somewhat similar if the system you're looking at is a set of satellites circling the moon or Jupiter, far away, or if it's a set of particles really, really small, you're not in that system. So if you simulate and organize, reorganize, manipulate, change that configuration, you are outside of the system. So you could take some measurements, do your simulations, and then put it back into the system. But that's what we call external computation. And for many, many reasons, it's a good idea to do internal communication, or internal computation, because you want the system to be able to run itself. And speaking of swarms, a lot of things that I'm showing has been work with many, many people, and that's those are the my local collaborators here. That's my group. Picture taken in this plaza, and if you want to meet some of these people, you just cross that bridge. I think they're having lunch right now without me, but I'm happy to be with you here. Yeah, so I hope the sound will work.
Simultaneously steering a large number of agents to goal positions is a common challenge, whether you are an ant army trying to defend your home, just trying to get home after work, a densely packed warehouse of robots delivering products to be packed and shipped, or a marching band demonstrating your skills.
Yeah, so I should warn you, there will be lots of teasers and clips. I did not try to go into all the details of all this work. This is like the intro to a 10-15-minute video that covers a number of different papers and so on, teasers. So I'd be happy to talk to any of you and follow up and answer questions and so on and so on. This is rooted in a multi-robot navigation that has a strong tradition in algorithmic geometry and robotics and so on and so on. This is a classical paper in this field. If you want to coordinate how these things work and what they do to step out of each other's way, that doesn't scale very well. So that classical paper is able to do these kind of things. You see here some configurations, but the computational effort, the algorithmic complexity grows exponentially with a number of robots. Obviously, that's not something we want to do. And here's another kind of object that actually came from Braunschweig here. So one problem that you're certainly faced is coordinating the object, the motion of many moving objects. How do you do this? Well, one, that's an autonomous car. Some of you may have been to California or to San Francisco in recent times, so there's these robot taxis now, but there's a lot of development behind this, like that and like that. The real complexity doesn't come from avoiding hitting obstacles and knowing where you are. It comes from coordinating many of these objects. So that is reasonably okay. But when you get to a situation like this, and we have all experienced this personally, physically, how do these different agents coordinate? That is the challenge. And there are a few more things when you have these self-organizing structures that are based on local rules and that they form bigger structures. Here's one, which is not something you really want. And when you look at this out from space, Yucatan and there's Houston. So when you look at this down from space, that's the kind of thing you see. And when you look at down at the ground, it may actually be something like this evacuation, and you get really, really big traffic jams. And even if it's not that bad traffic jam, here is a situation, let me run this, that you may have experienced yourself. You go along on the highway and the traffic is dense, but then you come to a stop, you see the brake lights, and you keep going. And let me start this other thing on the right-hand side. And there's this stop and go interaction. So here, this is actually something we took. But here you see there's some stop and go, and the traffic doesn't work so smoothly. We've all been there. I mean, when you go next time you go on the highway, I remember when we were doing this research, I was always happy coming back from the road because either I had good road conditions and I had reason to be happy, or I saw some terrible traffic jams and I was excited because there was some things to observe. So people have looked at this, like what is the interaction between these moving objects? And physicists have looked at this, and there's a number of very simple rules behind this. So when you look at, you're following this car, what's a safe speed you can do? That's the speed of the leading car. And then there's some adjustment based on the acceleration that you can do and the time and reaction time and so on. Very simple kinematics. And yeah, so the speed you want to do is basically a combination of how fast you can go. These cars look like they can go really fast. How much you can accelerate or brake, and what is safe in terms of the vehicle in front of you. And yeah, I mean, there's that, and robustness, stability. So you can look at this and have a little bit of noise added to the system. And when you get this little bit of noise, and that's a very simple update rule, when you get a bit of noise, this is the kind of picture you take. So that is space and that is time, and you see the color corresponds to the speed of the vehicles. As you go down, you see you go follow this trajectory, and then it slows down, accelerates again, goes like this, and you see when you go through this, this is stop and go traffic. So these waves that you're getting are self-organizing structures that you don't want, but even if you look at this, so that's a very, very simple simulation based on these kind of things in dense traffic. Okay, well, that's the world, right? And to go with another famous character from a space series, Jim, you can't change the laws of physics. Well, sometimes you can, because as a computer scientist, I had a background in physics at some point, and I was enjoying that, but physics is the way as the world as it is. And when you're a computer scientist, you want to change the laws, you want to change the interaction. So one of the things we did was looking at how do you change the interaction between these particles? And you can use wireless communication. Now, the question is, how do you actually use it? So you don't tell the cars, you go at this speed. If you have a large set, if you have different lags in communication and so on, that's not going to work. So we want something very simple, local, that updates these rules. And one of the things is, if you have some very simple aggregate information about the leading vehicles, about the ones that are in front of you, nothing fancy, nothing big, just the average speed in time of these, then you can actually use it, because what you just saw was basically some oscillation. And that's what you experience when you have stop and go traffic. It's oscillation. So we want to dampen this oscillation. And this is another equation that we just add to this mix. Basically, it's a convex combination of that and to the average speed of some sample of cars in front of you. So that, take the minimum, so you dampen this and you tell, like, don't go faster than the average speed here. It's not worth it. You have to brake. You will have to brake in a few moments. And this is actually what happens when you switch this on. So you see this is stop and go, and then at some point we switch it on and the traffic gets smooth. Even if there is stop and go traffic, you can do this. So it's much harder to fix something that is broken than to prevent it from breaking in the first place, but that actually works. And this is time now is going forward here, and you see what happens. It just makes things smoother and more uniform. And different view of this. So we go here. There's a big difference between the median and the average, which is that it's a very uneven distribution. A lot of people are standing, and we make this more homogeneous. And ironically, even though we tell people don't go so fast, the average speed increases because it's more homogeneous. And also, this is an interesting part, the fuel consumption. So the total fuel consumption, the red one, drops by something like 40%. Now, we actually got a patent on this. I should say we had a patent on this, because when we tried to talk to some car manufacturers, they said, we are good. We have our own ways of using computers to deal with exhaust and so on, in the diesel context in particular. And we understood a bit later what they meant. And I guess you all know how Volkswagen was able to optimize their exhaust around that time. At some point that, yeah. Okay, large structures. So that's a switch. And let me go play you another clip and trailer. So that's the International Space Station, and this is about building large structures in space. This is actually a relatively new DFG project we have, where we're cooperating with colleagues from MIT and NASA and so on to build large stuff in space. That's hypothetical, of course, but even if you want to build something really large in space, if you look at the ISS, That's about the size of a football field, and that has cost some $200 billion. Major expenses are getting the material up there, which is getting this in orbit is expensive. Getting it put together is expensive, doing this at scale. So if you want to build a large, even one large area of solar panels, like 1 square kilometer to get energy, or some people have these sci-fi ideas of shading the sun so we get cooled down here. That doesn't scale too well. So colleagues at MIT and NASA have developed these super light materials, which you can put them together. This is a bridge they built in the national park from stuff they carried in their backpacks, and you can do this at scale. Actually, the latest Artemis mission was announced to probably start, unless something happens, in a couple of weeks, or a bit more than a week. I think the latest data I heard was March 6th for the Artemis 2, and a couple of years later going to the moon. I took some pictures at NASA Ames last summer when I was there. When you watch solar missions, lunar missions about structures built there, permanent presence, so on, you may see some of these. I'm not involved in that. Obviously, that's a matter of national security in the US and so on and so on. But you can build these things with a density less than air in vacuum, because it's basically just the corners and the edges of these cells rather than solid matter. The second part is, how do you put that together using astronauts, which you briefly saw. Is very, very expensive, because astronauts are very fragile, and they need to be fed, and they need air and so on, and building something at scale doesn't really work so well. So robots. And of course, this is again, something that our colleagues in the US have built, where you have these small autonomous robots that can do these things. But then the next question becomes, how do these robots actually know what they do and where to move these things? And so this is from Houston with my friend and colleague, Aaron Becker. And then when you model this, come on, and you get some trailers, teasers. Ask me if you want to see more. So you can get these to change and configure and do this at scale with large numbers. And yeah, so if you want to move small objects, you can take tweezers. If you have many small objects, you can actually use an external global force, which is uniform, like a magnetic field. These microbes you can feed with iron particles, and then you use a magnet and they move. And you can use it on many of them simultaneously. One problem with that is that everybody moves the same way. So if you want to make them dance and sync, that's good. But if you want to reconfigure things, here, by the way, there's a way of moving things. These robots, these so-called kilobots, you can use an external light force to move them in one direction because they go to the light. So how do you break symmetry? If that's an A and you use the same global force, it stays an A because everybody's going in parallel. But you can break symmetry. So here the global force is gravity, by having some obstacles in the right way. And bang, like this. And keep going and turn the A into a B. Magic. There's a B waiting for us. It's a small b, got to be the same number of pixels. And there's more you can do. You can use different obstacles clockwise and counterclockwise. And you can also use another way of breaking symmetries using boundary interaction. So there's this thing about friction. And there are different ways of using these boundary interactions to get them into any configuration you want. That also works with physical objects. You saw that. And you can't fight the friction. Yeah, there's a few more applications which are not in space. So targeted drug delivery, if you have this global force and you want to not just flood the organism with all that, but you want to deliver them to particular places like to tumor sites. And you can also use that to actually put together in really small scale here. So these are very, very small particles, and you can, right, I need to speed this up. Many objects. Yeah, this is what other people have done. And let me just go one step. So we can do some things here. All this with bounded detours. Episode 2. So there's some things about not just moving these things around, but when you're in space, these things need to stay connected. Yeah, this is some other colleagues, and many of those you don't want to do this sequentially, but in parallel. And let me play you a little. So when you want to get from this side to that side, there's potential of having a large detour, but that could be very costly. And instead, if you manage to coordinate this whole thing well, you can do these kind of things, which is obviously, when it comes to time, much faster. Yeah, and you can do this in parallel, doing large scale reconfiguration with very limited local information. So you build some structures, scaffolds, and can turn the cup of coffee into a conference logo. And final one, I just saw the 5-minute mark. If you give me 2 extra minutes to those 5, I can show you an upcoming ICRA, that's the Global Robotics Conference, where it's something about tracking objects with minimal power by wireless stations. Oh, I should press the button, I guess. Does it work? Oh, come on.
We consider the problem of tracking a potentially large collection of moving objects, a fundamental problem with a long history and many important applications. In air traffic control, a typical scenario involves a number of stationary control centers, which are equipped with powerful tracking devices such as long-range radar, without much regard for the power consumption of tracking devices. With rapidly increasing number and ubiquity of small, lightweight drones, this type of air traffic control needs further development, such as the use of less powerful tracking stations. How should we adjust each sensor's radius over time to keep all objects covered while minimizing power consumption? Formally, we are given a set of moving objects, each following their own trajectory. We are also given a set of stationary tracking locations with adjustable sensor range. The challenge is to cover the moving objects with optimized power consumption that is proportional to the area of the disks. We assign radii to the stations, ensuring that every object is covered. The static problem is known as the disk covering problem and known to be NP-hard. By enumerating all possible assignments of objects to stations, we can solve the static version optimally using a set cover integer programming formulation. We developed an algorithm that can extend any feasible static solution to a dynamic one. In order to maintain feasibility, we identify event points at which the so-called supporting point of a disk changes. This allows us to maintain a feasible solution at all times. As one improvement, we identify event points at which it is cheaper to hand over an object from one station to another. This yields a cheaper solution across the full time interval. Now we can track the power consumption of our solution over time. We start with any feasible static solution and extend it to the full time interval using our algorithm. There are different objectives we can consider. One option could be to minimize the total power consumption over the whole time interval. However, for a large distributed network of sensors, it is also important to avoid undesired surges in power output. That is why we focus on minimizing the maximum total power consumption at any time. To derive lower bounds on this minimization problem, let's freeze time and look at a static instance at some arbitrary moment. For this snapshot, we can solve the static problem optimally with our integer program. That optimal solution is also a lower bound for that specific time. No solution, dynamic or static, can use less power at that moment. Now back to the dynamic setting. Our overall objective value, and thus our current upper bound, is determined by the time with peak power consumption. At this peak time, we again solve the static snapshot with the integer program. This optimal static solution gives both a cheaper solution and a lower bound on how low the best possible peak can be. We can extend this solution forward and backward in time. Now we have two feasible solutions. We combine them by taking the lower envelope. This produces a new schedule with a lower peak. Then we repeat. We identify the time with the highest power consumption and solve the static instance using our integer program. This time, the integer program solution returns a better lower bound to our min-max problem. Again, we extend this solution in both time directions. Finally, we merge both solutions to obtain a coverage schedule whose peak power consumption is only slightly higher than the current lower bound. We can iterate this process until an optimal solution is found, or the remaining gap is sufficiently small. In our work, we show that, even though the problem is computationally hard, we can still solve it effectively in practice using one of three proposed algorithmic approaches. Indeed, we are able to solve instances with up to 500 moving objects and 25 stations to provable optimality in just seconds, while the scenarios themselves play out over minutes in the real world. Here we see an instance based on a TSP-lib point set. We randomly sample 25 points as centers and compute a maximum matching on the remaining points. Now we see an optimal solution for a TSP-lib instance, showcasing both the efficiency and the strength of our approach. For more details, see our full technical paper.
I should say this video is about a week old, so this is the first time I'm actually showing it in public. Okay, thank you very much. And thank you for your attention. And if there's time for a question or two, I'd be happy to take it.
So thank you for your talk. We have time for one or two questions, right? Anybody?
Okay. That's fine. Thank you. Oh. So I should say this was a very, very broad spectrum, like a big buffet of our algorithmic work. So don't worry if you don't see the connections.
Yeah, I'm not from your area, and I'm just curious, does every robotics presentation go like this with lots of music and demonstrations? This to me seems very expensive.
Oh, that's a good scalability, right? Okay. It is also an aspect of expertise as well. The last video that you saw, actually, I've been doing these videos for 20, 25 years and so on. By now, There's tool chains where you can do some things like, oh, we need to change this word or that sentence. You go into the script, you change the word in the sentence, you press the button and you get a changed video because it's everything lines up and there's all this. This is the advantage of being computer science. I don't know if everybody does it, but I mean, yeah. I'd be happy to share some if you're interested, some tricks. I can what? Sorry, I didn't. Not accepted the challenge, but we'll see. Thank you. Sometimes I sing and dance in class for my students. I do first semester algorithms, so we can talk about that.